Good evening, everybody. Today, I am going to discuss about the grid generation under the computational fluid dynamics. Now, definition. Computational fluid dynamics, CFD, is a simulation of fluid flow using numerical methods. Think about the application. This variety of application actually makes us the thing very much clear about its utility in today's scenario. Firstly, aerospace engineering, automotive engineering, civil engineering, energy sector, marine engineering, heating, ventilation and air conditioning, chemical process engineering, biomedical engineering, environmental engineering, sports engineering, food and beverage industry, defense and military. Among this all, I am just citing few examples here, like the environmental engineering. I think now we all are very much familiar with this storm alert, cyclone alert. This particular thing actually comes from this CFD. The pressure velocity relationship and the trajectory actually helps us to find out, to give us the information about this cyclone update. Think about the defense and military, maybe in the space research also. We have to use some missiles, so we have to find out their trajectory path. That also very easily can find out by the CFD application. Think about the chemical process engineering. Suppose in our industry, we are using some reactor and it has some, suppose, or maybe some mixture and it has some impeller. 2-3 components you have to mix over there with certain concentration. Now, which particular impeller design, which particular energy is sufficient enough to mix these two components efficiently that we can done very easily without wasting any chemicals, without wasting any energy by using this CFD simulation. So there are lots of applications of this CFD in today's scenario. Now, from where it actually comes or from where it actually starts. In the year 1940, the foundation of CFD actually began. How? We all know that about the Navier-Stokes equation, which actually govern the fluid flow. The development of different numerical methods for solving these partial differential equations, we are applying that thing in solving the Navier-Stokes equation. Followed that, in the year 1953, the next step made by John von Neumann and its colleagues. What did they did actually? They developed the first numerical method for simulating fluid flow on early computers. Followed that, in 1960, NASA was exploring fluid dynamics for aircraft design. And they are inventing the finite difference method, FDM, and the finite element method, FEM. But that not actually the final one. In 1970, the development of finite volume method, FVM, that made CFD more practical for complex geometries. We can handle every complex geometry, every system. We can go for the analysis by using this finite volume method. During this time, the CFD moved beyond academic studies and began being applied to real-world problems, such as in aerospace, automotive, and industrial applications. Afterwards, in 1980s and beyond that, as computers become more powerful now, the CFD simulations become more accessible, accurate, and widespread with the development of commercial CFD software such as Fluent and CFX. And finally, The integration of this advanced turbulence model like KFCLL model, K omega model, and other different models and multi-phase flow simulations made CFD an indispensable tool in engineering design. Now, how we can do the work by using CFD? We can differentiate or we can divide the task in three different parts: the preprocessor, the solver, and the post-processor. Initially, we have to use the preprocessor. In preprocessor, we are actually creating the domain on which you have to do the calculation. So this domain actually the replica of the real one. But the thing is that without within this particular one, within this domain, what we prepared, we have to divide the domain. And this system known as grid generation. Now, what is the importance of grid generation? The accuracy and efficiency of CFD simulation are highly dependent on how the computational grid or maze is structured. They actually represent the discretized space where fluid properties are computed. So after we prepare the domain, we go for the grid generation. Then we can prepare the whole things. After that, we go for the solver. In the solver, we can use different solver, different models. We can go for finite volume method, finite element method, finite difference method, and go for different scheme like simple, simplex, presto, different things. You can go for up and down and scheme. And after that, after the solver, we are applying the thing in the post processor, getting the result like different plots, different contour plots, different velocity vector distribution, different trajectory path, path line distributions, everything. So finally, we can say that the first step is preparing a proper grid. Now, what is the grid generation? The process of creating a computational maze to solve fluid flow equations. Now, component of a grid is what? Nodes, point in the grid. Like this is a point, this is a point, this is a point, this is a point. And cells, regions between nodes. So this blank space, these are the regions, they are known as the cells. So a grid is actually a summation of these nodes and these cells. What is the objective? To divide the physical domain into smaller elements for numerical solutions. Just I want to go for a very simple example. Suppose we have here a flat plate and we know the temperature in this particular area, this particular site and this site. And we have to find out temperature of this particular point actually, maybe. So in that case, if we simply finding out this particular temperature from this and this point at this point, it will create much more amount of error. But if we go through from here to here by this grid generation, by this node base or cell base, it is much more easier to get the accuracy in the result. Now, types of grid. It may be structured grid, unstructured grid, and hybrid grid. What is structured grid? It is a regular ordered grid with a simple connection pattern. Just look here, there is a regular pattern we can show here. So if we have a uniform shape of any domain, we can simply go for the structured grid. The example is Cartesian grids. If we go for the unstructured grid, when? If we have irregular grid, more flexible for complex geometries. Suppose you have a pyramid shape, you have a cylindrical shape. You have a very complicated shape are there. So we cannot go for simply a Cartesian grids. We have to go with the triangular or tetrahedral grids, like this type of grids. Sometime, if we go for the hybrid one, when? If we are combining this both the one, structured and the unstructured, generally the structured grids in the interior and the unstructured grid near the boundaries. Just see here, throughout this interior there is a structured grid, regular shape, and here there is an unstructured grid, irregular shape. Now the grid generation methods. Structured grid generation, we can use regular grid with simple layout. It's very easy to generate actually. Uniform Cartesian grid or grids with stretching in some directions, cutting from one direction to another direction. We can do it very easily. Unstructured grid generation. Flexible grid suited for complex domains. Example, Delaunay triangulation, Voronoi diagrams. Multi-block structure grid. Grids is divided into multiple blocks for different regions, but each block is structured. And then the adaptive grid refinement, AGR. Mesh refinement in areas of high gradients near walls or sockets. Just think that you have a venturi meter. So, in the upstream section, we can very easily go for the Cartesian grid, the regular grid. But when we have a converging section or diverging section, in that area, there is a high gradient change. So, we have to go for the unstructured grid. Now, what are the challenges in grid generation? Firstly, the complex geometry. Actually, in real world, we cannot face the regular like a very easy shape. We are often intricate and difficult to mesh what we are getting in our real world. Then, based on that, to maintain the grid quality, it is again a much more difficult task because the poor grid quality leads to inaccuracy in the result and create problem in convergence. And if you cannot properly convert your result, convert your all the iterations, you will not get the accuracy in the result. So you have to think about the skewness, orthogonality, and the aspect ratio of cells. So we have to think about the grid refinement, ensuring the grid is refined enough in critical areas while maintaining computational efficiency. So I'm going to just elaborate this particular point. Actually, as I mentioned a few minutes ago about the venturi meter, similarly, we can cite that in a domain, if there is a continuous section where there is no so much change in gradient, so we can go for the regular grid or structure grid or coarser grid, or where we have a high gradient change, we have to go with the finer grid or unstructured grid or refining the grid. Actually, based on that, there is a test named as grid independent test. Generally, a particular review says that for any CFD simulations, actually 50% of time spent for creating an optimum grid for the process, and the remaining 50% actually using for the solving section and creating the further result. So I think that for this discussion, you have an idea that how much grid refinement is important in any CFD simulation. Now, how to create the structured grid generation techniques. Cartesian grid, we all know, regular and easy to generate, works well for simple geometries, normal cubes, normal boxes. Block structured grid, divide the domain into smaller blocks, each with its own structured grid. And it is again better for complex geometries. Then the curvilinear grids, used for more complex geometries like circular or curved shapes. This grid can conform to boundary shapes. But still, there is a limitation. So you have to go with the unstructured grid. And the techniques for that, first is the Delaunay triangulation. It is a very familiar method. Ensures no large angles between nodes, creating well-shaped elements. Voronoi diagrams used to create cells by partitioning space such that each cell is closer to its corresponding node than to any other. And the mesh generation algorithms. The algorithms like advancing front method, octree-based methods are very much essential in this particular area. Now, how to maintain this grid quality? What are the matrices of this grid quality? The skewness. This actually measures how far a cell deviates from an ideal cell. Then the orthogonality. It measures how perpendicular grid lines are to each other. The aspect ratio. It measures the elongation of cells, which is very much important. The cell quality. It affects the accuracy and stability of CFD results. Grid refinement and adaptive grids. Why grid refinement is needed? To capture important flow features like boundary layers or shock waves. If you cannot refine your grid at the boundary, you cannot properly understand the actual phenomena what is happening in the boundary layer. Now, the adaptive mesh refinement, AMR. It is dynamically refines the grid in regions where greater detail is required. So the benefit is we have to improve accuracy in critical areas while saving computational resources. I want to add one point over here that you may have a question, you may have a suggestion that we can refine every section the finer grid. But think that how much we can refine our grid, it will take that much amount of time to compute. And that create a burden to the computer system. So we have to optimize the grid. We have to maintain the accuracy. On the same time, we cannot give so much burden to the computer system. So we have to optimum the grid generation. That is the primary task of any CFD simulator. Now the application of grid generation in CFD. Aerodynamics, designing aircraft or car shapes, simulating the airflow. In turbomachinery, simulating the flow through turbines, compressors, and pumps. Within the compressor, how the thing actually going on. Within the turbine, how the thing actually going on. We can very easily compute by the inlet pressure, outlet pressure by this CFD simulation. And that helps us to further do the thing which is better for the process without wasting any chemical, any money for that. Then the environmental engineering, simulating pollution dispersion or weather patterns. In biomedical engineering, simulating airflow in respiratory systems, blood flow in arteries. So what are the different softwares are here for generating the grid? ANSYS, OpenFOAM, GMSH, Pointwise, Fluent, etc. So in summary, I can say that this grid generation is a fundamental part of CFD. It's impacting both the accuracy and efficiency of simulations. The structured, unstructured, and hybrid grid are used based on the problem's geometry. Grid quality and refinement are crucial for accurate results. And in the future trend, the adaptive mesh refinement and the automated grid generation are becoming increasingly sophisticated here. With this, I am just concluding this session here. In our next session, I am going to discuss in detail about the Delaunay triangulation. Thank you.